Welcome to this webinar on Immutable Linux in the world of embedded. My name's Joe Richmond-Knight and I'm a Field Applications Engineer for SYSGO. We'll start today with a brief introduction on SYSGO and follow up with some typical use cases for embedded Linux before moving on to some of the challenges that are faced with the deployment and maintenance of an embedded system. Next, we'll focus in on what an Immutable Linux OS actually is, and then talk a little bit about our Linux distribution, ELinOS. I will then provide a quick demonstration of how we can set up an Immutable OS before we wrap up this webinar with a summary of our discussion points. Now a brief introduction to SYSGO, who we are, where we're based, and what we do. SYSGO is the leading European operating system vendor for embedded systems, providing safe and secure technologies and services through our products like PikeOS, a hard real-time operating system and hypervisor, and ELinOS, an industrial Linux distribution. More on these later. Founded in 1991, we've been around for a while and know our customers' needs and challenges, especially when it comes to the certification of high-integrity systems, focusing on safety and security. Finally, since 2012, we've been part of the Thales Group, enabling us to maintain our European technology status with no export restrictions like ITAR. SYSGO is a global organisation based out of Europe, with our operating headquarters based in Mainz, Germany. We also have other European locations specialising in engineering and certification, for example. With this, we're able to meet the needs of our customers throughout their product lifecycle, from concept to maintenance. We also have a number of worldwide sales distributors supported in part by Thales. At SYSGO, we have three main products, complemented by additional resources to support your project. PikeOS is a hard real-time operating system and Type 1 hypervisor, capable of achieving the highest level of certification for both safety and security on all major MMU-based platforms. The unique combination of RTOS and hypervisor means PikeOS can host deterministic applications alongside general-purpose guest operating systems like ELinOS, whilst maintaining separation in both time and resource. We also have a variant of PikeOS called PikeOS for MPU, which targets processors with a memory protection unit only. Our second product and the focus for this webinar is ELinOS, an industrial-grade Linux distribution designed for embedded systems. We will cover ELinOS in more detail later. Finally, we offer supplementary products and services to support our customers, namely board support package development services, certification evidence kits for both our off-the-shelf products as well as BSPs, and other professional services like training and system architecture consulting, known as SysArch. Okay, now time to focus on some of the use cases of embedded Linux and the challenges faced. Before we dive into the use cases, we should first define what embedded Linux actually is. So in its simplest form, embedded Linux is the use of a modified general purpose or specialized Linux distribution with an end product to serve a dedicated purpose. This can be contrasted to a general purpose operating system, which is designed broadly to accommodate multiple functionalities. Some examples, therefore, are within IT equipment like data gateways and firewalls, industrial use cases like human-machine interfaces in heavy plant and manufacturing, Internet of Things systems like smart devices and data hubs, as well as entertainment systems like set-top boxes, games consoles, and smart speakers. It goes without saying that most of these systems are deployed on the edge, whether that edge is physically a remote location or whether the edge just refers to the separation between the end user and the system maintainer. There are a number of considerations, therefore, or I suppose challenges to be addressed when designing an embedded Linux system. Firstly, security. Since these systems are often deployed remotely, either on remote networks or in the case of offline devices, away from a physical means of protecting the device, how can the system be designed in a way that will ensure the integrity of the system and applications against malicious actors? Next comes reliability. For large embedded systems, you may expect a level of maintenance which in a way can accommodate for a lower level of reliability, but for many modern embedded devices, especially those that are low cost and low power, the reliability has a direct impact on the user experience. Therefore, how can we architect an embedded device to operate in a reliable, stable manner? Repeatability. It's important for the system to operate as intended, but it's also important for it to operate as expected, time and time again. This is a measure of system repeatability. Finally, maintenance. Many systems will require updates to improve security and features. How is this approach for embedded systems? As you can see, there are a number of challenges in designing a robust embedded system. In reality, many of these challenges listed form a blended set of requirements to build against. For example, reliability and security are often also improved through maintenance. Let's spend a bit of time going through what an immutable Linux OS is and the benefit it provides before taking a deeper dive into ELinOS as an immutable OS. Immutable as a word can be defined as something not capable or susceptible to change, and this ethos is central to an immutable Linux OS, described as an operating system designed to be read-only and not easily modifiable. These immutable operating systems have the following characteristics. System files are read-only, therefore any resource required, like libraries and files, are defined at build time. This is one of the fundamental principles of an immutable OS. Next, any files that are created, like logs and temporary files, are lost on a reboot of the OS. This may sound like a disadvantage at first, but presents a number of benefits which we will cover shortly. Updates to the OS are carried out holistically. For a typical general-purpose OS, updates may be rolled out with a package manager, where the base OS itself doesn't change, rather it evolves. For an immutable OS, however, the update replaces the whole OS image. Finally, immutable operating systems often rely on containerization of applications. This provides an additional layer of abstraction between the OS and the application. Let's now see how the inherent behavior of an immutable OS applies itself to the challenges we highlighted earlier, starting with security concerns. As an immutable OS is read-only, it's not possible to tamper with the underlying system. This greatly reduces the attack surface to methods of system exploitation like viruses. Further, if for some reason the system does become compromised, any malicious changes are completely lost on a system reboot, returning it to a known state. In terms of reliability, read-only systems typically cause less wear on the medium, like flash storage. Often the OS is loaded from non-volatile memory into RAM, and any temporary files are saved inside of a volatile RAM disk. Therefore, there's an inherent reliability upside when using a read-only system. Of course, this doesn't protect a system from OS file corruption, but this risk is the same across both immutable and normal operating systems. Repeatability is another main benefit of an immutable OS. Outside of embedded devices, immutable operating systems are often used as sandboxes for system development because they can be recovered from a broken state without a full reinstall of the OS. If the system is rebooted, the OS returns to its normal unmodified state. The same is true for the embedded use case, providing a level of repeatability over the duration of the system's life. Finally, the update and maintenance policy of an immutable OS is handled as a whole, where a single image containing both the OS and the application is updated. This simplifies the process and is especially popular in embedded devices. Now we're going to spend a bit of time talking about ELinOS and how it can be used as an immutable operating system. ELinOS is our industrial-grade Linux distribution, which can be used as a standalone product as well as alongside PikeOS, since they share a common IDE, which we call Cadeo. ELinOS provides a feature-based approach to build a lightweight embedded distribution with a strong focus on security. These features include I/O drivers, stacks for connectivity, some real-time extensions, as well as a focus on support for industrial embedded hardware. SYSGO also offers engineering services and support around the product, ensuring it can be maintained for long-term projects. Let's dig into a few of these topics in more detail over the next few slides. As I mentioned, ELinOS includes a graphical feature configurator in the form of our Cadeo IDE. This makes it incredibly simple and quick to configure an OS targeted for embedded devices in a way that can be stored and repeated for future use. Further, because ELinOS is feature-based, these OS images can be designed to be very resource efficient on both storage and processing. ELinOS includes a layer of abstraction which can be used to configure the Linux kernel to include the support for features required, whilst pairing these with the corresponding user space applications, configuration files and libraries. Finally, features are simple to add and remove. Gone are the days of having to manually remove individual packages and nested dependencies from a standard Linux distro. As ELinOS's configuration methodology is features-based, it's possible to create a system which is as small as possible. This greatly reduces the attack surface available to malicious actors. Further, ELinOS supports many standard security mechanisms like SYLinux and kernel memory protection. Technologies like virtualization and over-the-air updates strengthens ELinOS's position as a security-focused OS. As we expect systems that use ELinOS to be deployed for years and years, we provide long-term support, including maintenance releases of the OS. Whilst ELinOS is perfectly suited as an OS in its own right, it also operates perfectly as a guest OS on top of PikeOS, either in a paravirtualized or hardware virtualized configuration. This includes configurations like Secure I/O, where the guest has no access to the underlying hardware, or Direct I/O, where select peripherals are passed through to the guest. As PikeOS is highly portable across all popular architectures like x86 and ARMv8, as well as being highly certifiable for both safety and security, it's an excellent choice as a hypervisor for ELinOS. PikeOS also uses the same Codeo IDE as ELinOS, so there's a good user experience for the developer. Okay, so how does this all tie in? We're happy to announce that in the 7.2 release of ELinOS, we now have an out-of-the-box support for an immutable version of ELinOS. This includes a read-only base system, but extends the benefits of an immutable OS by also including built-in support for Docker containers. This both satisfies the immutable principle, but also allows the OS to be used as a kind of abstraction layer between the base hardware and a container environment of your choice. In other words, it becomes less about the OS and more about the application layer. This also means that, should you choose, you can manage the base immutable OS and the applications within the Docker container separately. So for example, the system may pull a container from a remote server on boot to ensure the most recent version is being used, and potentially fall back to a known baseline if there's no network connectivity. We'll now cover a short demonstration of how to set up ELinOS in an immutable configuration. Okay, here we'll work in Codeo 7.5 with a new workspace for the immutable OS demonstration. I'll create a new ELinOS project by using our pre-configured immutable OS template. So as a first step after starting Codeo will be to create an ELinOS project. We'll give it a name, select the ELinOS system project and click Next. And now we can already switch to the pre-configured immutable OS template. This is the immutable OS, so most of the configurations will be preset already. So we can select our BSP in board support packages. ELinOS comes with a wide collection of BSPs for several architectures like ARM or x86. We have the microchip PolarFire RISC-V BSP, we have PowerPC, but for this demonstration I'll click QEMU. So QEMU is our virtual machine that we can demonstrate everything on in the demo. And clicking Finish here, we'll wait for the configuration to load. What this will do is copy the project to the workspace and set up the configuration files, and this usually only takes a couple of seconds. There we go, done. Now we already have the project set up and the features available here for configuration. So for this configuration I will just change the input console because I'd like to have it displayed in the QEMU window. And also what is required for the immutable OS is to select the storage device which should be used for the Docker images. So for that we have a BSP specific storage support. This one's on QEMU based on VirtIO. So I'll just click Save here to make sure those configurations are applied. Now I change my feature configuration. And the next step is to open the file system configuration, because I've prepared a script which can run on the system to demonstrate that it's not possible to remove any files, modify the system init process, and therefore demonstrate that the system really is immutable. So that's actually already it for the setup. So I'll save and we can start the build process. What this basically does is compiles the Linux kernel, because it's available from the sources, and only the drivers which have been enabled by our feature configuration will be compiled. The user space applications like systemd or the Docker runtime engine is already pre-compiled, so these will be copied to the system. So the outcome of this build process, which we'll see in a moment, is a single file for QEMU, which contains the kernel and parts of the root file system as well as the base system. And this can be quite easily loaded into QEMU, and you'll see how we set up a remote connection in a moment. So while the kernel builds, we'll set up this remote connection. This is an additional plugin provided by SYSGO in our Codeo IDE to connect to a remote target system where there's an ELinOS or PikeOS instance already running, but you can also use it to emulate the target with QEMU. So we'll just give the connection a name, select the ELinOS version and the workspace that we're working against. And now if we click simulate target with QEMU, this means the QEMU virtual machine will automatically be started in Codeo when we connect into this system. So you don't actually need to do that on the console. So if I click finish here, a new remote system connection will be set up in the window in the bottom left, and we can use this to start our emulation. For the Immutable OS, we need to have some additional QEMU command line arguments. So this can be done here. And the text field allows us to enter some additional arguments. And mainly the arguments here are surrounding a writable ext4 partition required for the Docker environment. And that's because the base system is effectively read-only, but we need a writable environment for a container system. So the kernel is still building here and should be finished in a few seconds. Okay, so not too bad, about just under 3 minutes. So what we can do already here is start the QEMU session. So start the emulation of ELinOS on top of QEMU. And you can see this new window has popped up, coming up, showing the systemd as the system starts. I'll just wait for the OS to fully boot. And there we go, we've already got a shell, so we can log in. And now what I'll do is start the script that we copied over into the file system, which tries to modify the file system and therefore performs a number of tests. So please don't execute a script like this in real life, because it'll probably break your system, but I've just set this up here for demonstration. So it tries to get root access, which in this case works because I've already logged in as a root user. But the root file system is not writable, so it tries to mount in a read-write mode, but this is also not working. After that, it tries to copy the script itself to the file system, and this fails due to the read-only file system of the Immutable OS. It also tries to modify the startup scripts of the systemd process by adding a number of additional lines, but that, of course, is also not allowed, so that also fails. And as a final step, it tries to remove some critical files from the base system, If this would work, the system would no longer be usable, but the root file system is also not writable, so you can't modify any of these files. So with that relatively straightforward test, you can see that the system here truly is set up with an immutable configuration. The root file system is in a read-only state, and you can't change anything on the base system itself. Now let's wrap up with the value propositions on the next slide. The value of ELinOS as an immutable OS is the combination of the benefits of such a system for security, reliability, repeatability, and maintenance, paired with the ecosystem provided by ELinOS as a distribution, including the easy-to-use IDE, features-based configuration, and long-term project support. To summarize what we've covered today, embedded Linux is used across multiple industries for many applications, including IoT, HMI, and entertainment. Major challenges faced by the designers of embedded Linux systems surround security, reliability, repeatability, and maintenance. An immutable OS can address some of these concerns by providing a read-only, predefined OS environment which applications can be deployed on top of. And ELinOS is a lightweight, features-based Linux distribution with an out-of-the-box immutable configuration, extensible through the use of Docker containers. If you have any questions or comments, or just want to get in touch with SYSGO, please reach out to our team using the contact details below. Stay up to date by subscribing to our newsletter and following us on social media platforms.